What if the strangest visitor to our solar system did not arrive with a flash, but with a shrug, a speck of light logged, catalogued, and filed away while the real story kept unfolding in the background? In July 2025, astronomers spotted an object now known as 3I Atlas. It was moving too fast to belong here. Its orbit was not a long ellipse like a typical comet, but a one-way arc, a path that said clearly, this thing came from the space between stars. At first, the mainstream explanation sounded neat. Another interstellar comet briefly warmed by the sun, then fading as it headed back into the cold. Case closed. But as more observations came in, the story stopped being neat. A persistent dust shroud seemed to blur the nucleus, like a thin mask. Activity appeared to continue later than expected. Some images hinted at structured outflows that were hard to line up with simple sunlight-driven behavior. Nothing here is proof of anything extraordinary, but it is exactly the kind of pattern that makes careful scientists uneasy. So the question is not, is it aliens? The question is, why does this object resist the boxes we built for it? Why did the conversation cool down when the data was heating up? And what might we learn if we follow the measurements all the way to the end? Tonight we are going to track 3I Atlas from discovery to the latest observations and then forward to its critical encounter with Jupiter in March 2026. We will separate what we know from what we suspect, and we will keep the mystery intact, right where it belongs. Because sometimes the universe does not shout. It whispers, and the real test is whether we are patient enough to listen to it closely. The discovery itself was not cinematic, it was a workflow. Survey telescopes take repeated images of the same patches of sky and software compares them, looking for anything that moves. Most moving points are familiar: main belt asteroids, near-Earth objects, and ordinary comets on bound orbits. In mid-July 2025, one faint dot did not match the usual pattern. It was sliding against the star field too quickly, and its path did not curve the way a solar system object should. Astronomers flagged it, then immediately began follow-up. Early astrometry, the precise measurement of position over time, is the key. With enough points, you can compute an orbit. For 3I Atlas, the best-fit orbit came back hyperbolic. That word matters. A hyperbolic orbit means the object is not trapped by the sun's gravity. It came in with extra speed, and it will leave with extra speed. The sun can bend its path, but cannot make it stay. To refine the trajectory, teams pulled in larger instruments. Optical telescopes improved the position measurements. Radio tracking systems helped constrain timing and motion. Facilities connected to the Deep Space Network, built for spacecraft communication, can also support precise radio observations. The Green Bank Telescope, a powerhouse for radio astronomy, can help probe gas and dust signatures and track activity in a different part of the spectrum than visible light. As the data accumulated, the interstellar conclusions solidified. This was only the third confirmed interstellar object ever detected, after the earlier visitors that forced astronomers to admit the space between stars is not empty. It is a highway, and we are only beginning to see the traffic. At first, the natural assumption was simple. Interstellar objects should be odd. They formed around a different star, traveled for ages, and were exposed to radiation and collisions along the way. A comet-like body could have an unusual mix of ices. A rocky body could have a strange shape or spin, so 3I Atlas was logged, named, and watched quietly. And that calm beginning is important because what comes next is not a story of people inventing mystery. It is a story of an object slowly earning it. Inside the teams, the mood was a mix of excitement and restraint, but astronomers distrust first impressions. They ask practical questions. How bright is it? Does it show a coma, the fuzzy envelope of dust and gas that marks comet activity? Is the brightness changing in a way that suggests rotation? Can spectroscopy detect familiar molecules, the chemical fingerprints of ordinary comet ice? Even this early, a few details felt slightly off. The activity looked weaker than expected for a classic icy comet at the same distance. The light curve hinted at regularity rather than chaos, and the object's path, while consistent with gravity, seemed too clean, as if it had arrived with its aim already set. None of this rewrote textbooks. But it justified more telescope time, and it opened the door to measurements. Once the orbit was nailed down, the next question was physical. What is it made of, and what is it doing? To answer that, astronomers leaned on a toolkit that sounds abstract, but is basically common sense with better instruments. Photometry measures brightness over time. Spectroscopy splits light into colors to reveal chemical fingerprints. Imaging tracks the shape of the surrounding coma and any jets, streams of dust and gas leaving the nucleus. Radio observations can search for emissions that optical telescopes miss, and networks built for spacecraft tracking can help pin down motion with extreme precision. If 3I Atlas were a standard comet, the story would be familiar. As it approaches the sun, surface ice warms and turns directly into gas. That gas drags dust with it, creating a coma and a tail that points away from the sun, pushed by solar wind and sunlight. As the comet recedes, the heating weakens, outgassing drops and activity fades, but the datasets did not line up cleanly with that template. Brightness measurements showed periodic changes that looked more like a steady rotation than a chaotic tumble. Early analysis discussed a cycle near 16 hours, the object brightening and dimming with a regular cadence, as if the same regions were turning toward and away from us. Later measurements suggested that period might shift slightly, which could happen if the object is losing mass or if jets act like tiny thrusters, changing the spin. Either way, a stable rhythm implies a cohesive body with a consistent shape and orientation. Then came the dust. Multiple reports described a surrounding cloud dominated by particles in a narrow size range, around 10 microns. In optics, particle size matters because it controls how light scatters. A cloud dominated by one size can behave like a selective screen, bright enough to reflect sunlight and blur sharp edges, but thin enough to let the object keep moving without heavy drag. If that dust shroud is real, it complicates attempts to infer the nucleus size from brightness alone, because you may be measuring the glow of the shroud, not the solid core. Imaging also raised questions about jet geometry. Some observers described a double jet pattern and even an apparent antitail, a structure that seems to point sunward. In ordinary comet physics, sunward features can occur through viewing geometry and dust dynamics, but they are usually transient and sensitive to illumination. What made the discussion interesting was the claim that the feature persisted as the object moved outward and cooled, when activity should have been sputtering out. Finally, there was the motion itself. Most of the time, gravity explains comet trajectories extremely well, but with interstellar objects, even small non-gravitational forces matter. Outgassing can act like a weak engine. Radiation pressure can push on dust. If jets are sustained and directional, they can slightly alter the path. For 3I Atlas, the debate was not about a dramatic swerve, but about whether subtle deviations might be present and what would be required to cause them. Put all of this together and you get an uncomfortable conclusion. Even if every observation has a natural explanation, the combination is unusual. A persistent dust shroud, structured outflows, a stable rotating rhythm, and activity that seems out of season. So here is the mystery that hangs at the end of the data. Is 3I Atlas simply a comet from another star system that happens to sit at the weird edge of our experience, or are we looking at a kind of object we have not learned how to recognize yet? For now, when data refuses to fit, scientists do not jump to the wildest story. They widen the menu of natural possibilities first, and they ask which one requires the fewest new assumptions. The simplest natural model is that 3I Atlas is a comet from another star system. It may carry ices that behave differently from the water-rich comets we know. If its surface is coated with darker material, sunlight might heat it unevenly, producing jets from specific patches while leaving other volatiles trapped. A steady rotation could keep those patches returning to the same orientation, giving the light curve its rhythm. Another natural possibility is that it is not a classic icy comet at all, but a mixed body, partly rock, partly ice, with a crust that vents gas through narrow cracks. In that picture, the activity could stay organized longer, because the vents act like nozzles. That could also explain why some emissions appear directional and persistent. A slight shift in rotation period could follow naturally from torque, the tiny twisting force produced by jets acting off-center. The dust shroud can also be interpreted naturally. Comets can release dust in preferred sizes depending on how grains stick together and break apart. If the nucleus sheds material through a particular fracture pattern, it could produce a narrow particle range. The cloud of similar grains would scatter light in a particular way, making the object look larger and fuzzier than it really is. In other words, the mask might be an accident of physics, not a choice, but every natural model has pressure points. Directional jets that persist far from the sun require a power source, and in comets that source is usually sunlight. If activity is still strong while the object cools, you must explain what is still driving sublimation or gas release. You can propose trapped supervolatiles, ices that evaporate at low temperatures, but then you must explain why their spectral fingerprints are not obvious. You can propose crystallization of amorphous ice-releasing gas, but that mechanism would still need to match the measured dust production and the timing of the jets. This is where more speculative ideas enter, not as claims but as stress tests. If an object behaves as if it has a preferred orientation, sustained outflows, and a shroud that hides the nucleus, some people ask a provocative question: what if it is not purely natural? What if part of what we are seeing is engineered, like a thin dust cloud used to control temperature or shield a surface? What if a jet is not outgassing, but exhaust? A few high-profile voices have suggested using the object as a test case for a broader idea, that technological artifacts might travel between stars quietly without broadcasting radio messages. In that framing, a dust veil could be camouflage, and a precise trajectory could be navigation. Even this can be approached scientifically, by asking what signatures a thin sail, an exhaust plume, or an artificial surface would leave in spectra, in polarization, or in acceleration. Over long weeks, the artificial hypothesis has a serious weakness. Extraordinary claims need extraordinary evidence, and we do not have direct evidence. No clear signals, no resolved structure, no unambiguous non-gravitational acceleration. And nature can be weird, especially when we are looking at a sample size of 3. So the honest position is this: natural explanations remain the default, but they are not yet complete. Artificial explanations remain speculative, but they highlight exactly which measurements would matter most. In a way, both paths lead to the same conclusion. We need better data, and we need to keep watching. All of this brings us to the next major waypoint, Jupiter. In March 2026, 3I Atlas is expected to pass through Jupiter's gravitational sphere of influence. That matters because a flyby is like a natural experiment. Gravity is predictable. If you know the mass of Jupiter and the incoming path of the object, you can forecast the outgoing path with high precision. Any mismatch, even small, forces you to ask what extra forces were at work. Scientists will be watching for 3 main things. First, trajectory. Does the object follow the expected bend, or does it drift in a way that suggests non-gravitational acceleration? Even a tiny push, sustained for months, can leave a measurable fingerprint. Second, activity. Jupiter is far from the Sun compared to the inner solar system. If jets and dust production continue strongly at that distance, it strengthens the case that the driver is not simple sunlight heating. If activity drops sharply, it supports a more ordinary comet story. Third, physical diagnostics. During certain geometries, telescopes can measure how light is polarized as it scatters off dust. That can reveal particle sizes and shapes. Spectra can also change with distance, hinting at which volatiles are still escaping. If the dust shroud thins, the nucleus might become easier to constrain. There is also a wild card. Jupiter's gravity can stress an object slightly. If 3I Atlas is fragile, tidal forces could change its rotation or trigger new outbursts. If it is cohesive, it may pass unchanged. Either outcome is informative. Observers will coordinate across facilities, because different wavelengths answer different questions. Optical telescopes can track shape and brightness. Radio dishes can probe gas, if any is detectable. Timing measurements from tracking networks can sharpen orbit fits, and even negative results matter. If no gas is detected, that is a clue. If no acceleration is measured, that is a clue. In orbital terms, Jupiter acts like a slingshot, boosting the object's exit speed. That makes this encounter the last checkpoint before the trail fades into the dark. The point is not to predict drama. The point is that March 2026 may be the last time we can learn anything decisive. After the Jupiter encounter, the object will continue outward, growing fainter, colder, and harder to observe. Whatever 3I Atlas is, it is leaving. The question is whether we use this final window to turn mystery into knowledge. So where does that leave us? 3I Atlas arrived as a faint moving point and quickly became something rarer than a visitor. It became a challenge. Its interstellar orbit told us it came from beyond the Sun's domain. Its brightness rhythm suggested a stable rotation. Its dust and jets, at least as reported in follow-up analysis, raised questions about what powers its activity and what we are truly seeing when we look at it. We explored the conservative explanations first, because nature earns the benefit of the doubt. A comet from another star could have unfamiliar ices, unusual dust, and vents that stay organized. Jets can torque a nucleus. Dust clouds can hide boundaries. And with only 3 interstellar objects in hand, the phrase normal behavior is almost meaningless. But we also acknowledge why the object keeps pulling attention back. Some features seem too persistent, too structured, or too out of season. That does not prove design. It does not even imply it. It simply means the data is still speaking. In March 2026, Jupiter provides our last strong chance to listen. After that, 3I Atlas will slip into the outer dark, and we will be left with whatever measurements we were wise enough to capture. Maybe the final answer will be ordinary, and the mystery will dissolve into better comet physics. Or maybe 3I Atlas will become the first example of a new class of interstellar object, something that forces us to expand our vocabulary of what can drift between stars. Either way, this is the point. The universe does not owe us clarity, it offers us clues. The rest is patience, curiosity, and the courage to keep looking, even when the story refuses to end. What else is passing by now unseen while we argue about certainty?